Welcome back to another deep dive here at the Rooster Podlog. This time we're going deep, really deep into the core of big data processing, specifically within Apache Spark.
Sounds exciting.
It is. I've got some really, really fascinating material here, and I think our mission today should be to really unpack how Spark plans and executes its work, under the hood.
I'm all for that. It's a pretty amazing system when you start to peel back the layers.
Absolutely. So to kick things off, where do you think we should start with that fundamental blueprint, the Spark DAG?
Yeah.
I know it's a core concept, but maybe we could go from the basics to, some of the more nuanced aspects.
Yeah, the DAG is really where it all begins. It's like the foundation of Spark's ability to handle these massive data sets. So starting there makes a lot of sense. And yeah, we can definitely layer on the details as we go.
Perfect. And then from there, we can dive into those powerful engines, right? Tungsten and Velox.
Definitely, we'll explore their strengths, their weaknesses, and where each one really shines, especially Velox, since it's creating so much buzz for OLAP workloads.
Exactly.
Yeah.
It's all about building that solid, intuitive understanding of Spark's inner workings.
Right, and exploring those innovations that are making it faster and more efficient all the time.
Okay, so let's start with the Spark DAG. In the simplest terms, what is it?
Well, at its core, the DAG, or Directed Acyclic Graph, is Spark's execution model. So when you tell Spark, hey, I want you to filter this data and then, let's say, aggregate it, Spark doesn't just jump into action right away.
It doesn't.
Nope. Instead, it creates a logical plan first. And that plan is the DAG. It's like Spark's way of saying, okay, here's the most efficient way to get this done.
So it's like a roadmap.
Yeah, exactly. Think of it like a really detailed map for your data's journey through all these operations.
Okay, I'm starting to get the picture. So if the DAG is the map, what are the key landmarks, like the nodes and edges?
Good question. So the nodes, those are the actual transformations you want to perform, like selecting specific columns, filtering out rows that don't match your criteria, maybe joining different data sets.
Okay, so the nodes are the actions, the verbs.
Right. And then the edges, those are the connectors. They show how data flows from one transformation, one node to the next.
Got it. So the edges are like the arrows on the map, showing the direction.
Precisely. And the directed part simply means data flows in one direction, no going back.
But a one-way street.
Exactly. And then a cyclic, that's super important. It means there are no loops in this plan. Your data won't get stuck going in circles, endlessly repeating transformations.
Okay, so it's a directed one-way flow without any loops. So before Spark even processes anything, it maps out the entire journey the data will take using this DAG.
Precisely. It's all about planning and optimization before any real work happens.
That's pretty smart. So how does Spark actually use this DAG to get the job done?
Well, that's where the DAG scheduler comes in. It's like the project manager, right?
Mm-hmm.
It takes that high-level DAG, the map, and breaks it down into manageable chunks called stages.
Stages. What defines a stage?
Shuffle boundaries.
Shuffle boundaries. Okay, you're going to have to explain that one.
Sure. Think of it this way. Sometimes, to complete an operation, data needs to be rearranged across the different machines in your Spark cluster.
Oh, okay.
Yeah, like if you're grouping data by a specific key, that data might be spread out. So it needs to be brought together. And that redistribution is called a shuffle. It's a big operation, so it marks a clear break between stages in the DAG.
So a shuffle is like a major reshuffling of the deck, and that's where one stage ends and the next begins.
You got it. Within those stages, the work is divided further into tasks, the real workhorses of Spark.
So if stages are like chapters in the plan, tasks are the individual paragraph or sentences, the nitty-gritty details.
Yeah, that's a great way to put it. And each task works on a specific partition of your data.
Okay, remind me, what's a partition again?
Oh, right. It's basically like dividing your massive data set into smaller, independent chunks. So each task is responsible for processing one of those chunks within a specific stage.
Okay, so we've got the overall plan, the DAG, broken down into stages, and then those stages are broken down further into tasks that work on individual data partitions. Wow, it really is a structured, organized process.
It is, and that structure is a big part of why Spark is so efficient.
I can see that. But I'm curious, why go through all this planning up front? What are the real advantages of this whole DAG approach?
Well, this is where the real magic happens. This approach enables some really crucial optimizations.
Okay, like what?
Well, first, you have lazy evaluation.
Lazy. So Spark's taking it easy.
In a way, yes. Remember how Spark builds the DAG first without actually executing anything right away?
Yeah, it's like planning the route before starting the journey.
Exactly. That means Spark can analyze the whole sequence of operations, figure out the most efficient way to do things, and then, and only then, does it actually start crunching data.
So it's not just about having a plan, it's about having the most optimized plan possible.
Exactly. It's like a general strategizing before a battle, taking into account all the variables before making a move.
Smart. What else?
Then there's pipelining.
Pipelining, like those big oil pipelines?
Kind of. For certain operations, those called narrow transformations, Spark can execute them together, in a sequence, within a single task. It's super efficient because the data just flows through, like, without any pauses or redistribution needed between those steps.
So it's streamlined, no stopping and starting, just continuous flow.
Precisely. And that's a lot faster than treating each operation in isolation.
I can see that. Okay, so we've got lazy evaluation and pipelining. What's the third big advantage?
Fault tolerance.
Which is super important in a distributed system, right?
Absolutely. Things can go wrong, nodes can fail,
Yeah.
but because Spark keeps track of the lineage of each RDD, each piece of data, it knows exactly where it came from and what transformations it went through.
It's like a detailed history log.
Exactly. So if something fails, Spark doesn't have to start from scratch. It just recomputes the affected parts using the lineage.
That's incredibly clever. So the DAG approach gives us lazy evaluation for optimization, pipelining for efficiency, and fault tolerance for resilience.
You got it. It's a powerful combination.
It really is. I think I'm starting to grasp this DAG thing, but I always find that analogies help solidify things. What about that Lego castle analogy you mentioned? Can we walk through that?
Oh, I love that analogy. It really helps visualize everything.
Perfect. Let's do it.
Okay, so imagine you're building this awesome Lego castle, the Spark DAG. That's your detailed instruction manual.
Okay, the instruction manual, got it.
And each Lego brick, that represents a partition of your data.
Right, so lots and lots of bricks for big data.
Exactly. Now, the different pages in the instruction manual, those are like the stages in your DAG. So you might have one page for the gatehouse, another for the walls, and so on.
So the stages are like logical sections of the building process.
Precisely. And those specific steps on each page, those are your tasks.
Yeah.
Attach brick A to brick B, things like that.
The tasks are the super detailed instructions, the atomic actions.
Exactly. Now remember, lazy evaluation. It's like you, the master builder, not rushing into building right away. You take your time, study the whole manual, understand the entire design.
Right. Getting the big picture before diving into the details.
Yes. The DAG scheduler, it's like it divides the manual into those logical sections, the stages. Some steps you can do in sequence, smoothly, like attaching small decorations. That's pipelining, efficient assembly line work.
Makes sense.
But say you need to attach a big tower to the main gate.
Okay, I can see where this is going.
You might need to coordinate with someone else who's building the gate. That's a wide transformation requiring a shuffle, like exchanging Lego pieces between builders.
Right. So the shuffle is when different parts of the build need to come together.
Exactly.
Yeah.
Now imagine disaster strikes, someone knocks over a tower. No problem. You have the instructions, the lineage. You just rebuild that section using the instructions. No need to start the whole castle over. That's fault tolerance.
Wow, okay, I love that. The Lego castle analogy really makes it click. So we've got the plan, the DAG, and we understand how it gets broken down and executed. But how does Spark actually run those tasks? This is where those powerful engines come in, right?
You got it. Let's talk about the first one, Tungsten.
Perfect. What can you tell me about Tungsten?
Well, Project Tungsten was this, huge leap forward in optimizing Spark, especially when it's running within the Java virtual machine.
The JVM.
Yeah. You see, the JVM is great. It provides platform independence, but it also comes with some overhead, Yeah. And that can slow things down when you're dealing with massive data sets.
Right, there's always a trade-off.
Exactly. So Tungsten was all about making Spark on the JVM truly viable for big data. And it did that by tackling those JVM overheads head on.
Okay, so how did it actually do that? What were the secret weapons?
Well, one of the most important things Tungsten did was change how memory was managed.
Okay, memory management. How so?
So before Tungsten, Spark used the JVM's heap for storing and processing data. But that meant it was subject to garbage collection.
Garbage collection. Isn't that a good thing?
It is, but it can also cause pauses. Imagine the JVM is like cleaning up and organizing, and everything has to stop while it does that. Not great for performance.
Ah, so Tungsten found a way around that.
Exactly.
Yeah.
It introduced off-heap memory allocation, so Spark could manage memory directly, outside the JVM heap, bypassing the garbage collector, making things smoother, faster.
Like having a separate workspace for certain tasks, avoiding those interruptions. Brilliant. What else?
Other big innovation was the unsafe row binary format.
Unsafe row. Sounds a bit dangerous.
The name's a little misleading. It's actually all about efficiency. You see, in the JVM, data is often represented as Java objects, which have some overhead, extra information that's not really data, just baggage.
Okay, like metadata and stuff.
Yes, unsafe row is this super compact, specialized format that cuts out all that unnecessary stuff. It's like packing your suitcase really efficiently, you know?
Right, so more data in the same amount of space and faster to move around as well.
You got it. Especially during shuffles. Remember those? Unsafe row makes those shuffles much faster.
That's a big win. Okay, so we've got efficient memory management and data representation. What else is in Tungsten's toolbox?
Well, there's also this really cool concept called whole stage code generation.
Okay, write that down for me.
Imagine, instead of executing each tiny operation as a separate function call, you could combine multiple operations within a stage into one optimized chunk of code.
Oh, so like batching them together.
Exactly. Tungsten does that. It compiles multiple operations into optimized JVM bytecode at runtime.
Runtime. So it's doing this on the fly.
Yep. It's super dynamic. And it eliminates those function call overheads, lets the JVM optimize things better, and ultimately makes things run faster.
So it's like taking a series of individual steps and combining them into a single, fluid, super efficient move.
Yes, precisely. It's a real game changer.
Wow, Tungsten sounds like a real workhorse, tackling all these optimization challenges. Anything else?
One more big one. Tungsten also incorporates techniques for cache-aware computation.
Okay, cache-aware. What's that all about?
It's all about taking advantage of how the CPU works. The CPU has these caches, right? Small, fast memory areas. And cache-aware computation means designing things so that frequently accessed data is kept in those caches.
So it's like keeping the most important tools close at hand.
Yes. It reduces the need to go all the way to main memory for that data, which is much slower.
Makes sense. So it's about optimizing for data locality, making sure the data is where it needs to be when it needs to be there.
Exactly.
Wow, Tungsten really did a lot to make Spark on the JVM as efficient as possible, tackling memory, data representation, code execution, and data locality. Very impressive.
It was a big step forward. But, it's important to remember that Tungsten still operates within the constraints of the JVM. And it's fundamentally based on this row-based execution model.
Row-based, meaning it processes data one row at a time.
Right. And for certain analytical workloads, especially those where you're only interested in a few columns across a massive number of rows, that can be inefficient.
I can see that. If you're only analyzing a few columns, you're essentially processing and moving a lot of unnecessary data, the whole row.
Exactly. And that's where Velox comes in, offering a completely different approach.
Okay, let's talk about Velox. It's Meta's next-gen engine, right? And it uses this thing called vectorized columnar processing. Can you explain that in detail? What makes it so different?
Sure. So while Tungsten works with data row by row, Velox processes it in batches, in columns. These batches are called vectors. Think of it like, instead of dealing with one Lego brick at a time, you're working with entire trays of identical bricks. Same type, same color.
Okay. I like where this is going.
Right, that's vectorized execution. And the columnar format means that data is organized by column, so all the values for a specific attribute across many rows are stored together, instead of grouping all the attributes for a single row together, like in the row-based approach.
So instead of organizing the Lego bricks by the item they belong to, you organize them by color or ship.
Yeah, precisely. And this might seem like a small change, but it has some major advantages.
Okay, I'm intrigued. What are the benefits?
Well, one of the biggest ones is how it affects CPU cache utilization, especially for analytical queries. You see, in OLEP-LP workloads, you're often analyzing just a few columns, but across a huge number of rows.
Right, like looking for patterns across a specific attribute.
Exactly. And with the columnar format, the data you need for those columns is all stored together, so it's super fast for the CPU to access and process.
It's like if you need all the blue bricks for a particular step, you just grab the blue tray instead of searching through boxes of mixed bricks.
Perfect analogy. It eliminates so much wasted effort.
That makes a lot of sense. You're only bringing in the data you actually need. So better cache utilization. What else?
Another big one is SIMD optimizations.
SIMD. What's that?
It stands for single instruction, multiple data. It's a way for the CPU to perform the same operation on multiple data elements within a vector, all at the same time.
Oh, so it's like parallel processing at the chip level.
You got it.
Oh,
It's like having multiple robotic arms attaching the same type of Lego piece simultaneously. It massively speeds up a lot of common operations.
That's amazing. So columnar storage plus vectorized execution, that's a powerful combination. What else does Velox bring to the table?
Well, it also incorporates adaptive runtime optimizations.
Adaptive, so it can change its approach on the fly.
Exactly. Velox can actually adjust the execution plan based on the data it's processing. It might reorder operations, choose different algorithms all in real time to optimize for the specific characteristics of the data it's working with.
Wow, that's incredibly intelligent.
It is. It's like the engine is learning and adapting as it goes along.
Okay, that's impressive. Anything else?
One more key feature is dictionary encoding. This is especially helpful for columns that have many unique values, but also lots of repetition.
I've seen that kind of data, lots of repeating values.
Yeah, it's common. So instead of storing the full value every time, Velox creates a dictionary of unique values and then just uses references to those values. It's a bit like using abbreviations.
Right, so it saves space and makes comparisons faster.
Exactly. And on top of all that, Velox is written in C++ base,
C++ C.
not Java. Nope. And that's a big deal because it completely sidesteps the JVM and all its overhead.
No more garbage collection pauses, right?
Gone. Plus, C++ gives you more control, allows for some really deep optimizations that just weren't possible with the JVM.
So Velox is like a whole new generation, a complete rethinking of the execution engine. It's not just about optimizing within the existing framework, it's about creating a new framework altogether.
That's a great way to put it. It's a fundamental shift.
You know, I really want to make sure I'm grasping the magnitude of this difference between Tungsten and Velox. Can we go back to the Lego analogy for a minute? So, if Tungsten was like a highly skilled builder, using all the best techniques and tools, but still placing individual bricks, what would Velox be like?
Okay, so Tungsten is the master craftsman. They've got all the skills, the perfect organization, the most efficient movements. But Velox is like a highly automated, state-of-the-art construction machine. Think giant robotic arms, pre-assembled modules, the whole works.
Wow, okay, that paints a very different picture.
Right. The expert builder might be, say, 2 to 3 times faster than a novice, but that machine can be 10 times faster, maybe even more, especially for complex projects.
So it's not just about being a little bit faster, it's about a fundamental difference in how the work is done.
Exactly. It's about scaling up in a way that simply wasn't possible before.
Okay, that makes a lot of sense. So when would you choose one engine over the other? Are there situations where Tungsten might still be the better choice?
Absolutely. Tungsten's been around for a while. It's mature. It's stable. It's integrated into a lot of existing systems. So for many general Spark workloads, it's still a great choice.
Especially if you're not dealing with massive, complex analytical queries.
Right. If your performance needs are already being met by Tungsten, there might not be a huge need to switch to Velox. It might even be more complex to implement.
Right. Sometimes it's about using the right tool for the job.
Exactly. Now, you mentioned OLAP workloads, and that's where Velox really shines.
Why is that? What makes it so well suited for those kinds of analytical tasks?
Well, remember how we talked about OLP involving analyzing just a few columns across a massive number of rows?
Yep, the classic needle in a haystack scenario.
Right. Velox's columnar data format is perfectly suited for that. It can retrieve and process those columns super efficiently, minimizing the amount of data that needs to be moved and processed.
Right, because all that data is right there together, nicely organized.
Exactly. And then there are complex aggregations and window functions, common in OLAP. Velox's vectorized processing can handle those incredibly efficiently, working on large chunks of data in parallel.
So it's not just about storage, it's about how those analytical operations are performed.
Precisely. And then there's joining multiple large tables, another common task in OLAP. Velox, being written in C++ Word, just excels at that.
Because it has lower level control and can implement those really optimized algorithms, right?
Exactly. And we can't forget about memory efficiency. That columnar storage format is often much more compact for wide tables, which is essential when you're dealing with massive data sets.
Right. Keeping that memory footprint as small as possible is crucial.
Absolutely. And then on top of all that, Velox has those adaptive execution capabilities, dynamically optimizing query plans based on the data.
So it's constantly analyzing and adjusting for maximum efficiency.
You got it. It's all about making OIP workloads run as smoothly and as quickly as possible.
And I remember you mentioning some pretty impressive benchmark results from Meta. Can you remind us what those were?
Yeah, Meta reported some really amazing performance gains with Velox for OLAP. On average, interactive analytical queries were 6 to 7 times faster. And for some Very complex, CPU-intensive operations. They saw speed-ups of up to 10 times compared to their previous engine.
That's huge. So for anyone working with big data and doing those kinds of analytical tasks, Velox seems like a real game changer.
It really is.
One last time for our listeners, can we revisit the Lego analogy in the context of OLEP?
Absolutely. So
Mm.
if OLP is like analyzing the castle, not building it, Velox's approach is all about looking at similar components across the whole structure. Like first analyze all the towers, then all the walls and so on. It's column-oriented analysis.
Okay, so looking at the data vertically rather than horizontally.
Yes, exactly. And those aggregations we talked about, it's like having a tool that can instantly summarize all the bricks of a certain type and color across the entire castle. And the memory efficiency means you need fewer trays to organize those bricks because you're focusing on one type at a time.
And the adaptive execution is like the analysis tool changing its strategy based on what it finds, right?
You got it. So it's a fundamentally different approach, and for large-scale analytical workloads, it's remarkably efficient.
Okay, so we've gone from the Spark DAG, the Blueprint, to Tungsten, the master builder, and now to Velox, the advanced machine. It's been quite a journey through the evolution of Spark execution engines.
It has, and it really highlights the constant drive for performance and efficiency in big data.
Absolutely. And for our listeners, I think the key takeaway here is that the future of big data processing is moving towards this columnar vectorized approach. Velox is a prime example of that, and it's something to keep an eye on.
I completely agree. It's going to be exciting to see how these engines continue to evolve and what new innovations emerge in the future. Who knows what kinds of specialized machines we'll have for processing data in the years to come.
Maybe we'll be talking about quantum Lego castles one day, but for now, I think that's a great place to wrap things up. Thanks for taking us on this deep dive into Apache Spark.
My pleasure. Always happy to dive deep into the world of big data.
And for our listeners, we encourage you to explore these engines further. Understanding how they work can give you a real edge in the world of data analytics. Until next time.